Okay, let's dive right into this explainer. Today, we're going to explore one of the absolute most mind-boggling pieces of space trivia you'll ever come across. We're breaking down the fascinating physics, the super precise orbital mechanics, and, honestly, the surprisingly complex human biology behind a fact that gets thrown around all the time, but is rarely fully understood. So, if you've ever found yourself wondering how humans actually live and work in the extreme chaotic environment of low Earth orbit, well, you're in exactly the right place. Let's get into it.
You've probably heard this famous fact, right? The incredible piece of trivia that astronauts aboard the International Space Station witness exactly 16 sunrises and 16 sunsets in a single Earth day. It sounds deeply romantic, doesn't it? Almost poetic. 16 new dawns, 16 golden hours, all completely compressed into just 24 hours. It's one of those wild statistics that gets repeated in almost every article ever written about life in orbit, and yeah, it is absolutely accurate. But to really understand what that number actually means for the people living up there, we have to look at the math.
So why does this relentless cycle of day and night happen? Well, it's because the station is just absolutely rocketing around the Earth at a blistering 28,000 kilometers an hour. That is a speed that's honestly almost impossible for our Earthbound brains to truly visualize. To put that into perspective for a second, at 28,000 kilometers an hour, you could cross entire continents in the time it takes you to brew a pot of coffee in your kitchen.
And at that jaw-dropping speed, the International Space Station and its crew complete one full lap around the entire planet roughly every 90 minutes. Just think about that. In the time it takes us down here to watch a short movie or play a single game of soccer, these astronauts have completely circumnavigated the globe. They've passed from the glaring, unfiltered light of the sun straight into the pitch black of the Earth's shadow and then right back out again.
Moving into Section 1, the physics of 90 minutes. Now, what's really interesting here is the sheer contrast. You see, the time it takes to orbit a planet is entirely dictated by altitude. Take an object in a geostationary orbit, like a communication satellite. It sits way out there, about 36,000 kilometers up, and at that massive distance, it takes exactly 24 hours to lap the Earth, which is exactly why those satellites appear to just hang motionless over one specific spot on the ground. But the ISS? It sits in low Earth orbit, just 400 kilometers above our heads. Because it's so incredibly close to the Earth's gravitational pull, it literally has to move that fast just to keep from falling back down into the atmosphere.
So, the absolutely crucial point here is that this 90-minute orbital period isn't some weird quirk of the space station's design. It definitely wasn't a choice made by engineers just for the fun of it. It's entirely dictated by the hard physics of its low altitude. Lower orbits are faster. Higher ones are slower. The math is absolute.
Which brings us to Section 2, what the numbers leave out.
Because when you actually peel back the layers on this famous trivia fact, you realize those 16 sunrises are one of the most commonly misunderstood things about the space station. Hearing about 16 sunrises makes it sound like the crew lives 16 very fast, highly compressed, miniature days. You might picture them working for a few hours, sleeping for an hour, and waking up to a new dawn and doing that over and over again. But wait, actually, scratch that. Those sunrises are literally just the view outside the windowed cupola module. Because the station is moving so incredibly fast, the actual sunrise itself only lasts for a few seconds. The full swing from daylight into the total darkness of Earth's shadow and back out again, that fills that entire 90-minute orbit. So it's a visual phenomenon happening outside the glass, not some biological reality happening inside the ship.
And this perfectly illustrates how numbers are so often rounded up for the public. If you use the European Space Agency's much more precise telemetry, which puts the station's speed closer to 28,800 kilometers an hour and gives us a 92 to 93-minute orbit, the arithmetic actually comes out to about 15.5 orbits a day. But let's be honest, 16 sunrises is just a way catchier soundbite than 15.5 sunrises. So 16 is the number that's stuck like wildfire in the public imagination.
But wait, it gets even weirder. The Alpha Magnetic Spectrometer team, they've got this cutting-edge instrument riding on the outside of the station. They note that this sunrise count isn't even a constant thing. During what physicists call high beta angle periods, which pop up each summer and winter, the angle between the station's orbit and the sun actually climbs above 70 degrees. And when that happens, the station's path doesn't pass into the Earth's shadow at all, for days at a time. The station is just bathed in constant perpetual sunlight. The orbital sunsets literally just stop altogether.
All right, on to Section 3, keeping time in space.
So, if the sunrises are happening in mere seconds, or sometimes disappearing completely for a week during those high beta angle periods, how in the world does the crew actually keep track of their days? With absolutely zero usable, consistent cues from the sun, the station relies on a single, unwavering clock set to Coordinated Universal Time, or GMT. And get this specific time zone wasn't chosen for some deep astronomical reason, it was chosen specifically because it serves as a perfectly neutral geographic midpoint between American mission control in Houston and Russian mission control in Moscow. It's essentially just an administrative compromise to bring some order to the orbital chaos.
And despite the absolutely chaotic solar environment flashing by right outside their windows, their internal schedule maps out a stubbornly normal 24-hour day. We're talking a scheduled wake-up time, followed by a totally standard working day of conducting brilliant scientific experiments and doing routine station maintenance. They have scheduled meals, mandatory exercise to keep their bone density up, and a solid sleep period carved out for around 8.5 hours. Inside the station, it looks surprisingly like just a regular Tuesday back on Earth.
Which leads us nicely into Section 4, tricking the human body.
Because, as you can imagine, knowing when to sleep on a spreadsheet is one thing, actually convincing your body to do it while floating in zero gravity is a whole other challenge. Maintaining that rigid, earthbound schedule requires some very deliberate engineering hacks to completely trick the human body. To shut out the madness of 15.5 blinding sunrises a day, NASA had to get really creative. They installed specially designed LED lighting throughout the station that actively shifts its color temperature and brightness to fake the slow progression of an Earth day. It sounds like super advanced space travel, but honestly, it ultimately comes down to hiding in a dark, telephone booth-sized box wearing standard-issue earplugs and an eye mask, just aggressively pretending you're still back home.
And this quote right here really hits the nail on the head. The purpose of all of it is to supply the day and night signal that the planet below is no longer providing. Because the actual planet spinning 400 kilometers below them is offering up its light way too often and way too quickly to be of any biological use whatsoever to a human being.
I mean, think about how terrible you feel after just a few hours of regular old jet lag. Now imagine your core temperature and your sleep cycles trying to fight off 15 fake sunrises every single day. Over a very, very long stretch of evolutionary history, our bodies, our hormone releases, our core temperatures, our sleep cycles, they've been deeply, permanently tuned to the 24-hour rotation of Earth. So we end up with this amazing paradox. The crew of the International Space Station can only survive in space by actively, aggressively ignoring the very sunrises they are so famous for experiencing. They literally have to block out the reality of space just to maintain the reality of their own biology.
Which leaves us with a pretty incredible, expansive thought to ponder as we wrap up this explainer. If human biology is so profoundly locked into the slow 24-hour rotation of just one specific world, how in the universe will we adapt when we finally leave its orbit for good? Think about when we set up permanent bases on the moon, where a single day lasts almost a whole month, or when we travel to Mars, or venture even deeper into the dark. Our technology can easily escape Earth's gravity right now, but the real question is, when will our biology truly be able to leave Earth's time? It is a fascinating challenge for the next era of space exploration. Keep thinking about that, and I will catch you on the next explainer.